like I've shown here on the left-hand side, we have some daily temperatures from around the UK, the min, max, and mean over a 10-year period, well, 5-year period. And then on the right-hand side, we have some financial indices. We have exchange rates between various currencies and the pound, also over 5 years. But, you know, these are just 2 examples, and you can have almost anything else, any financial index or sales data, many things of interest, really. And it doesn't even have to be a series of like numerical values. It could instead be something more discrete. Like, for instance, well, still numerical, but you could have a look at the Bank of England interest rate, which is discretized and changes over time. Or you could just be looking at trends. Say, does the FTSE 100 index go up or down over a 1-day period? So there's a lot of freedom and a lot of things that you may be interested in. But how do you approach forecasting? Well, normally it's treated as a supervised learning problem. So you collect some kind of historical data set of whatever it is that you want to predict. And then you collect some information about some useful features which you think would be useful in making that prediction. So then you train a model, you test it, you find some correlations that help you make predictions, and you kind of hope that they will remain in the future. Although when you actually deploy your model, you probably want to monitor it to make sure that it continues to perform well. And that's it. Although there are other options available. You know, you could treat it as more some kind of unsupervised learning problem. So you can sometimes use clustering to, for instance, look at find different states of a system that you want to forecast, and then kind of identify which state you're in to figure out what's going to happen next. But in any case, we probably want to have a big historical data set, and we want to find some patterns. So that's the key goal. Now, one of the main approaches to forecasting is autoregression. And what that means is that you use past values of the series in order to predict future values. And this makes sense because many time series don't jump around completely randomly. You know that the temperature tomorrow will be something like the temperature today and the temperature the day before that. So if you collect your series, you can transform that into some sort of table of your target and your features. So here we have 5 previous values of the series under study on the left-hand side, and then on the right-hand side we have a column for our target. And we can train any regression model we like on this, really. It could be very simple, it could be linear regression, or it could be a tree-based model, or it could be something fancier still, like some sort of neural network or whatever model it is that you like. So in that way, it can be very similar to some of the things that we covered in the previous modules. But there are some other models as well that you may want to think about. One of them is ARP. So, well, this is actually just like linear regression. ARP is an autoregressive model that uses p previous values of the series in order to forecast the next. So here we have some linear weighting of the previous values with some error term, which is normally drawn from a normal distribution. So when we want to forecast the next value in the series, we just draw from this normal distribution. And if we want to get some kind of confidence intervals about our prediction, well, then we can, study the various different areas that we might end up on this curve, and figure out, just exactly what percentage confidence do we have in our value taking on any particular value in a range. So that's ARP. But it can only really be used on stationary time series. And time series is stationary, strictly speaking, if all moments of its probability distribution are invariant in time. Now, you may not know what that means, but for our purposes, mainly we care about something called weak stationarity. And that basically means that the mean and the variance don't depend on time. So really, wherever we look in our series that we're studying, we're clustering around the same value, and we're fluctuating around it with the same sort of variance. And this places certain restrictions on the model. So for instance, with this AR model, that requires us, if it's an AR1 model, that requires the magnitude of our weight to be less than 1. Otherwise, the series would be explosive and would be trending away from whatever mean it is that we're looking at. So what does that mean? Well, it means that the kind of series that we're looking at is actually sort of boring looking. I mean, this is an example of an AR1 process, and it looks a bit like random noise. It isn't really random noise, and if you look closely, you can see that the values tend to, they don't jump suddenly completely from one place to another. One value is kind of similar to the previous value. So we do have this sort of correlation in time, which you can see on the right-hand side. But still, it doesn't really look like the series that we wanted to study at the beginning, which were, this seasonal data here, or this exchange rate data, which has some long-term trends. Still, it can be useful, particularly for studying fluctuations that the model has around a trend or around its seasonal pattern, which we'll go into more a little bit later. There is an alternative to AR1 or AR, which is a moving average model, which has a bit of an odd name, because you might think that a moving average model would involve calculating moving average and then use that as a forecast for the next value in the series. But this standard model, MAQ, moving average with Q previous values, really actually uses Q previous values of whatever noise term it is that we're generating to forecast the next value in the series. So it kind of expresses a correlation where a noise term doesn't act at just one moment in time. It has some effect at a limited number of future times. And so this produces a series that, again, looks pretty random, but does have some correlations, although they're much more limited in time, because beyond the value of Q, which in this case is 1, the correlations in the series drop immediately to 0. There's simply no correlation on a long-term time period in this series. But again, kind of a not so interesting looking series. And you can combine this with AR to produce that ARMA model. And again, it looks pretty boring. But what we really want to do, obviously, is we want to be able to model something, like I said before, something with seasonality and trend. And the way that we can deal with that, at least let's begin with trend, the way that we can deal with trend is by differencing the series. Well, this is just one approach, there are others, but it's a very common approach. And if we take the difference between neighboring values in our time series, then we may end up with something like we see on the right-hand side here, where we've gone from a non-stationary time series, which is trending upwards over time, to something that clusters around a mean and doesn't really move away from that. You may see it's not completely stationary yet because the variance is varying in time. It's particularly large during, say, coronavirus or the financial crisis or other periods like that. But it is at least closer to the stationary series that we started out with our intention of studying. So what we can do is we can combine differencing with the ARMA model to produce ARIMA. ARIMA stands for autoregressive integrated moving average, and it's an ARMA model applied to a series which has been differenced d times. So first you difference the model, then you train your ARMA model, you make a forecast, and then you can integrate back your forecast points in order to create the forecast of the original series. And if you combine all the terms together, you have an equation that looks a little bit like this one at the bottom of the screen. But you don't generally have to worry about this too much, because when you are using this model in practice, you can just, well, you'll probably be importing it from some library, like stats models, and you can just train it automatically without really caring too much about what the equation looks like. But that's just for dealing with trend. and we are also interested in seasonal data. And to account for seasonality, we may instead want to look at seasonal autoregressive or seasonal moving average models, which are very similar to the previous ones that we've studied, except that the terms that they use from the series are now spaced by some seasonal period, S. So for instance, a seasonal ARP model would look like this, with adding up previous values of the series that are each spaced by S. And SMAQ looks very similar, except now it uses the noise term. And the Q seasonally spaced previous values of the noise term. Now, if you combine all that together with the non-seasonal components, you get ARIMA. And what does that look like? Well, it looks like that. It doesn't really matter too much, but that's the equation. And if you take your series and if you train your ARIMA model that you've imported from whatever library it is, then you can actually start to produce some forecasts that look like some data that you might encounter in daily life. Like here we have UK national grid demand, or the monthly mean of that over a 10-year period. And training it on the first 7 or so years, we can then create a forecast for the next 3 years, which does reproduce the seasonal 12-monthly period that we would expect. And it also has this downward trend, showing how our energy usage is trending downwards in time. So, much more kind of realistic and familiar in life than the original AR and MA series that we were looking at. But I think that's it now for, well, okay, no, we're not quite finished. The other big question with these models is how to actually choose all the hyperparameters, PD, Q, and capital PD and Q. There are many different combinations that you can choose from, and it can be very hard to figure out exactly what to do, especially since you don't want to overfit your model. And you know that the more parameters you have in your model, that is, the larger you make all these values, PDQ and PDQ, the better your model will fit. But it won't necessarily indicate that the model is more effective, just because, it's, you've just overfit to whatever training data it is that you've used. So in order to be able to select between different models, we can instead use something called the Akaike information criterion. And this criterion is basically an estimate of how much the distribution of our predictions from our model will differ from whatever the true distribution it is from the data that we are trying to forecast. And what we do, if we're trying to select between different values of these parameters, is we simply choose the model which minimizes the AIC. And since the AIC has a kind of penalty term within it that penalizes the total number of free parameters, this will tend to act against any overfitting and can quite effectively throw out some models that are too complicated really to be generalized to unseen data. Okay, so yeah, that was it for ARIMA and related models. But now I think we can talk a little bit about smoothing models, because sometimes we're not interested in the high frequency fluctuations in the series. We're not really interested in the noise that, or what appears to be noise, that we were looking at with AR and MA. What we really want to do is we want to throw away that noise to get a better estimate of the average value of the series at any point in time, to get a true representation of the state of the system under study. And there's a few ways of doing that, but one of the main ones is to use exponential smoothing. So exponential smoothing is a type of autoregressive model that creates a smooth series by creating a weighted sum of the observed value of the series with the previous value of the smooth series. And the weighting is controlled by alpha. And so the larger alpha is, up to a maximum value of 1, the less we filter any noise from the series. If alpha is 1, then we're just reproducing the observed series. But choosing a smaller value of alpha will tend to kind of mix in the observed value of the series with the smooth series, and each individual observation has a smaller weight within that smooth series. So it tends to filter out any high frequency fluctuations. And if you apply that to, say, the FTSE 100 index, you can see you can throw away all of the high frequency noise, and you just have this general trend in the orange. However, what you might notice is that this smooth series is really just following the observed series, and it's not really able to make any kind of forecast. Whenever the blue line rises, the orange line follows up a little bit later, and when the blue line falls, the orange line falls as well, and also later in time. So you may not find it that effective if you want to make a forecast. And instead, you may want to look at something a bit more complicated, which is the Holt exponential smoothing model, which can also incorporate a trend. So in this case, the smooth series is not only a weighted sum of the observed value and the previous value of the smooth series, but also includes this B term, which is the trend, which is calculated at any moment in time in the series, and which is also calculated via some kind of exponential smoothing. And if you do that, then you find a smooth series which hugs much closer in time to the observed one and responds much more to any changes in trend. Although if you choose the wrong value of beta, the smoothing parameter for the trend, you'll find that the smooth series tends to kind of overshoot or undershoot the observed series because it doesn't respond quickly enough to changes in the trend. But still, this is maybe not that effective if we apply it to seasonal data. So here we have quite a common time series data set that you may find on Kaggle or in examples of various time series libraries. This is the US airline passengers numbers in thousands from the 50s. And if we apply this Holt exponential smoothing model to this series, we get something that looks pretty similar, but again lags quite far behind the true observed series, and so actually isn't very good at forecasting. So instead, we will add in some kind of seasonal correction, which is expressed via this C term here, which is kind of a ratio of the observed value of the series and the smooth value of the series from the seasonal period before, and is updated by exponential smoothing, as with the trend and the smooth series. And I mean, in summary, basically it allows you to create a smooth series which can predict, based on seasonal periodicity, where the observed series will be, and is a much more effective fit to our data set. So yeah, in summary, we've covered two of the most basic forecasting models that you may encounter on your time series journey. We have ARIMA and Holt-Winters exponential smoothing. They can handle time series with trend and seasonality, and the form of the model can be chosen using the Akaike information criterion, which allows you to choose between different models and kind of penalize the more complicated ones, which you would expect to just overfit to the training data. But also, I should point out that there are many, many other models to look at. For instance, when you have a series where the variance is changing in time, you may want to, instead of looking at ARIMA, you may want to look at something like ARCH, or generalized ARCH, which I won't go into here. Or you could use some completely unrelated model like CatBoost or LightGBM. If you kind of transform your time series into some kind of tabular data set with columns of features and your target column. But yeah, I think now we can move on a little bit to talk about how you would validate a forecaster and how you avoid some common pitfalls that occur with time series data. So first of all, in a normal kind of regression or classification project, you would expect to randomly shuffle your data set to eliminate any kind of bias and produce fair samples for training and testing. And then in, say, k-fold validation, you would divide the data set into multiple training and testing sets where you don't really care if the training data comes from after the testing data or from before, because there's no concept of time in all these examples. You have no idea when exactly they were collected, and you don't care if one was collected before or after another. They're all independent. But of course, that is not the case in a time series. Time series have correlations in time, and that's the entire point of these autoregressive models that we looked at before. So because they have correlations in time, if you transform your series into some kind of tabular data set, you would expect neighboring rows of the data set to be quite similar, simply because, yeah, the value at yt is very close to the value at t+1. So if you randomly select rows of your data set for training and testing, you're gonna get overfitting, and you won't be able to detect it. If you overfit to the training set and then you evaluate on the testing set, you won't see any overfitting because the testing set contains examples that are already very, very similar to the training examples. So your forecaster will look very, very good, and then you will try it in the real world and it'll be terrible, or it could be terrible, and this will be completely undetected beforehand. So one of the main, most important things to do with time series data is to not shuffle it in this way. You need to keep it in order, and yeah, make sure that that the testing set is always taken from chronologically after the training set. So yeah, this is an example of data leakage. So information from the testing set entering into the training set. And it's always a problem really in machine learning projects, but it's especially a problem when working with time series. Another problem that you may find, another kind of data leakage, is when information is used for training that is available in historical data, but it is not available in production. So to give an example of that, excuse me. Well, I was going to mention, but I forgot to mention. Okay, in order to avoid data leakage, yeah, you keep the training set in order, and you may even want to create some kind of embargo period between the training and testing set, where you don't use this data at all, because it can create some overlap between information in the training and testing set. So anyway, apart from that, we want to also talk about this example of data leakage that I was talking about. So basically, you don't want to use information for training which is unavailable in production. And this is a very easy trap to fall into, because in hindsight, you have so much information about what was going on in the past. So for instance, if we had some kind of data set of sales from a particular shop, over the past year or so, and this data set also included information about the footfall and whether or not that day, any day, was a weekend or a holiday, then we may use this information to train a forecaster for sales. But then what we would fall into is the trap that actually we don't know the footfall for this day ahead of time. So if I want to forecast the sales tomorrow, I don't know what the footfall will be tomorrow. How am I going to run the model? This may be quite an obvious example that you would think of avoiding, but still, there are so many different ways that this can occur that sooner or later you may fall into this trap. You may be dealing with weather data, and of course you don't know the weather ahead of time with with certainty. I mean, you may have another forecast of the weather over the next few days or months that you might use when running your forecasting model that you've trained to rely on weather data, but that's going to introduce additional uncertainty. Also, sometimes you'll be training your forecaster based on company records that weren't released until a few months after the thing that you wanted to predict. Or you may be using sort of mobility data that is publicly available from Google, but they don't release that on a daily basis. They release that on a monthly basis. So in all these cases, you have to really think quite carefully about what you have available when you actually want to run the model. Yeah, okay, so in summary, we should only train our model on features which will be available at the moment we want to make a prediction. And the data set should not be shuffled because correlations in time will tend to cause leakage between training and testing sets. And also the testing data should tend to follow after the training data. I don't think this is kind of universally applied, but it is quite dangerous to use testing data from before the training data, since if in training you teach your model about correlations that are effective on the testing data from the past, your model may appear very good, but in actuality it won't be able to act well in production because, of course, the data that you're training on is from prior to the data that you're predicting on. So you got to be careful of that too. Okay, so that's really it for the slides section. And I think now we can have hopefully a bit of a demo. So if you'll just give me a moment. Okay. So I prepared a demo of predicting the NASDAQ index. So this is an American stock index, a kind of composite index of many companies. And we have a data set that includes a timestamp for each day. We have the opening price, the closing price, the high, the low, and the volume of trade. And we want to predict the opening price. And we're going to phrase this as a regression problem. And we need to make sure that our platform knows that we're dealing with a time series so that it doesn't shuffle the data and do all these things that I was just explaining are a problem. And we can select our context window, which really tells our platform how many previous values of the features in our data set can be used in the forecast of the target. So a context window of 5 means that we can use 5 previous values of the opening price and 5 previous values of the closing price and so on as features for our prediction. And then we have to choose how to split the data. Obviously, in any machine learning project, you have to retain some data for testing at the end to make sure that you haven't overfit your data. But also, you have to retain some data for tuning the hyperparameters. So we'll retain 20% of data for a final test at the end, which will be completely unseen until the end of the trial. And then we have different methods of splitting data for tuning the hyperparameters. And we have sliding window and expanding window, which are 2 quite common validation methods instead of k-fold cross-validation that you will find in time series. But we're going to stick with holdout because it's a bit faster. And we're going to choose a few different models for our trial. We're going to keep it with all these different linear models. We have basic linear regression, but also various Bayesian kind of alternatives which use different priors on the weights for regularization. And yeah, and we're going to hit start. So at this point, our platform, EvoML, will pre-process the data set that we've provided. It will generate those lagged features the 5 previous values of whatever features it is that we provided. and it will do some feature generation. And then it will begin the process of tuning the models that we've selected and tuning their hyperparameters. So far we have linear regression. And if we take a closer look at linear regression, we can see, say, for instance, a graph of predicted value versus true value. And we see a pretty linear relationship over there, which is what you would expect, really. I mean, you want this line to be basically true value equals predicted value. So you want y equals x. And what we find is a root mean squared error of 73 on the validation data that we use for hyperparameter tuning. Unfortunately, the value on the testing set is not as good, but that's pretty typical in machine learning. And then we can compare with all the other models that we have. So by now we've trained and tested a few more models, and now the current best one is Bayesian ridge regression. So similar picture really, but slightly better on the root mean squared error, and with a mean absolute error of about 45. And we have all these other metrics that we can use as well to examine the data and the performance. R2, Pearson coefficient, Spearman coefficient, and also the normalized training and prediction time, which can be quite important if you want to deploy your model. Sometimes you need a model that is very fast in prediction if you need to use it on a very regular basis. So yeah, that's pretty much it for the demo. It's still going on. It's still training models. And we can get to train hundreds if we wanted to. But at a certain point, basically, you would start to overfit the data. So, overfit the hyperparameters. So really, we don't need to run it forever. And I think we've already done pretty well. Okay, so that is that. Yeah, I think we can take questions now. Yeah, I think so. The chat is open, right? So anyone can type questions into there. Okay, we have something. Okay, no, it's just Roxana. That's fine. Yeah, recursive neural networks are one of the kind of more basic sort of deep learning models that can be used for time series. We do have an LSTM regressor available on the platform, which is a kind of current neural network. Yeah, deep learning models can be very effective, but they also need large amounts of data. So if you're working with a small data set, you may want to stick with something a bit more simple, like linear regression or the tree boosted models. And these also have some advantage of being a bit more explainable, because it's very clear exactly which features are most important in the forecast and how the model is making a decision. So for explainability, we can go to the Bayesian ridge regressor, and oh no, the graph didn't work. But yeah, we can typically, for many models, see feature importances that will tell us exactly which features are the most relevant in any particular forecast. Yeah, so overfitting and data leakage kind of come hand in hand in many cases. So the example I gave where neighboring rows of the data set are very, very similar is an example of data leakage where it makes overfitting undetectable when you then look at the testing set. So yeah, I would say they are quite closely related in some cases. And as for the API, I think, yeah, the engineering team has been working on an API to use the platform. But yeah, I'll have to ask a bit more. And I think we can send a follow-up email about that if you're interested in the platform and how to use it. Sorry, I don't know what. I don't understand the question about data serving. Okay, data leakage. Well, yeah, so embargoing your data is important. So having a gap between the training and testing set. I mean, not shuffling the data. There's not really one method to avoid data leakage. There's just a series of things that you have to go through. And probably the hardest thing to deal with is features which you thought would be available in production but actually aren't, because this takes a real kind of careful thought and understanding about what exactly it is that each feature in your data set means. So really, you just have to take due diligence. Yes. Okay, so the difference between time series regression and time series forecasting. Well, actually, forecasting is a kind of regression. So I guess the point really, I mean, the difference in the name of time series regression and time series forecasting on the platform is really it kind of controls which models are available. So for forecasting, we generally be doing kind of more longer term forecasts, multi-step forecasts, and we can do that with, say, ARIMA or exponential smoothing or so on. But then the time series regression pipeline is more focused on single step forecasts for a kind of prepared sort of tabular data set. Are there any possibilities where data leakage happened but still gives the expected results? I mean, it's not kind of impossible for you to have data leakage and then have a model which is kind of effective in production. It just makes it less likely for that to happen, I would say. You can easily have a model that looks like it works when you're testing it, but actually it doesn't work. But that doesn't mean that it will always fail. But still, yeah, it's important to avoid data leakage so that you can be a bit more certain of the effectiveness of your model ahead of deployment. But actually, even if your model looks like it's very effective when you're testing it, you still have to monitor it when you're deploying it, because there's really no guarantee, especially with time series, because things change. Like the environment can change, the financial market can change. There can be large external events which will change whatever patterns it is that you were using in your forecast, and suddenly your model doesn't work anymore. So I'd say it's always really, really important to monitor the model in deployment. Cool. Well, that may be the last question.